today, and one, I put together your test for Friday, and two, I reworked some of the slides to optimize helping you get ready for the test. So if you want to find the slides that I'm talking about, this is the 1092 informal understanding slides. And I think I have a link from the 2001, but if that doesn't link, you can go to the 1090 slides. Then come over down here, down, computing. See, we're doing computing for 2001 is about computing. So we hit there. And then let's go through these computing slides. And my hope is if you follow the, somebody mute themselves. Excellent. Nope. Somebody is making a lot of noise. There, I muted him. All right, so there's a first set of slides talking about computing, and then a second set of slides talking about using a more complex proof. And in order to do the assignment, you really only need to understand the first half, but if we have time, we'll do the second half. All right, so what do we know about computing? So historically, Hilbert talked about computing in 1900 in Paris, and Gödel came along in the end of this in 29 and said, well, you know, we don't have any hardware for computing, but we do have logic. So he designed a lot of the thinking about computation using logic. And so here are some of our parts. We're going to have various variables, and we want to think about how to interpret them. All right, so here, P is going to be a computational problem. And what's a computational problem down here? We say, well, for example, it could be the sorting problem. Sorting is a computational problem. And then what does it take? It takes I as an input. I is the input. And, you know, if we're doing sorting, then the input is an array of values. But when we're computer theorists, we always assume that the input's a generic binary string, but for the purpose of logic, it doesn't really matter. All we're knowing is I is representing the input. And then what is P of I? P of I is the required output when you have input I. So for example, sorting I is going to be the same numbers as in I, except sorted, right? Now, what does computable mean? Computable means some algorithm can compute it, right? So here, let A be an algorithm or a machine. Sometimes I use M for machine, and when I'm assuming it's a Turing machine, I use M, and when I assume it's an algorithm, I use A, and sometimes when I'm assuming it's a Java program, I use J. So what's an example of an A? Well, insertion sort is an algorithm, right? And so that's what I'm saying. Theorists always assume that it's a Turing machine, but for our purposes, we can assume that it's Java code. All right, so then what is A of I? It's the output produced by algorithm A on the input, right? So if insertion sort is bug-free, then it returns the sorted list. All right, so something's beeping. I don't know what's beeping.
Your Discord, sir.
I think it's your Discord.
It's your Discord.
Discord is beeping. Hey, Chester, are you in there? Do you know how to turn off Discord?
If you right-click on the icon, you can mute it for as long as you want.
All right, I think there's something down here. Is one of this one? Is that Discord? Quit Discord. Well, there, I'll just quit Discord. All right. We're back here. All right, so there's so many computer things I have to learn to do these Zoom classes. All right, so if an algorithm, we're talking about algorithm A computing problem P. What do we need if algorithm A is computing problem P? Well, we need that the output of A is the required output, right? So here we're going to write this. A of I equals P of I. What does that mean? That means algorithm A on input I gives you the same answer as problem P requires on input I, right? Which is a good thing. So now when we're talking logic, well, these P and N, oh, there's an N, sorry. See, that N's supposed to be an A. So this P and this A and this I are just variables, and this is a relationship between them, right? So you can see I did a global change of A's and M's to A's, and I failed. All right, so now this woman here is going to give us some deep understanding, and we're going to try to build a first-order logic sentence. So what do we want our sentence to say? We want it to say, we want P to be a free variable. So we're going to write a sentence that P doesn't have any quantifiers, and it's going to be about P. And we want it to say that P is computable. So what does it mean to be computable? Well, it means that algorithm A computes it, right? Computes P. So what we can write here, well, which algorithm, right? Which algorithm computes P, right? Here we can ask, are we saying that there's at least one algorithm that computes P, or does every algorithm compute P, right? Well, clearly, we're not saying every algorithm computes P. We're saying that there exists an algorithm that computes P. And then, well, what does it mean for algorithm to compute P? Well, before it can do any computing, you need an input, right? So we can say algorithm A solves P on input I. Now, which input I? Which I are we talking about?
All
is it at least one input, or is it every input? Well, it's every input. Remember, this upside down A is for all, while this backwards E is for exists. So it needs to be every input. And what does solve mean? Solve means it gets the right answer, right? Does that make sense? All right, so now the order in which you put these operators, these quantifiers, really matters, right? If you've been listening to the videos, which you should have done by Monday, then you certainly should know about these quantifiers, right? So if you put it first, then there exists one algorithm that works for every input. And if you put this first, then for every algorithm, there's a different, if you put this first, then for every input, there's a different algorithm, which would be kind of weird. All right? So the order you put them in changes the game. All right, so this little adversary guy, he says, hey, you better have one algorithm that works for every input, right? You can't have a different algorithm for every input. And hence, that's why we have this line up here. This says there exists one algorithm that works for every input, right? Does that make sense? Now, what does each, now we can say what one of the things that she does is she unwinds this sentence at different levels and sees what it means. So just this sentence, it has the three free variables. And what does it say? It says algorithm A correctly solves problem P on input I, right? And what does this say? Now it only has two free variables. So what is it saying? It's saying something primarily about those two variables. And we only talk about I as an afterthought. And what does it say about A and P? it says algorithm A correctly computes P. Notice we stopped mentioning I because it was sort of assumed. And then here, we added the exists in A. So now our only free variable is P. And so what is it saying? It's saying computational problem P is computable. Right? Does that make sense? And so now, if you've read all the videos, you know that there's a game that I love, right? How does the game work? Well, the blue guy, he's the prover, and he's investing in proving that the sentence is true. And what does he do? Whenever there's a, how does he prove it's true? Is if there's an exists, then he produces the algorithm to prove that it's true, right? Conversely, the adversary is invested in proving that the sentence is false. And how does the adversary do that? Or maybe if not proving it's false, at least giving the prover the hardest time possible. And so how does the prover do that? Is by, whenever there's a for all, producing the I that makes it hard, right? The worst case input. All right, and then who wins? Well, the prover wins if this final relation is true, right? Does that make sense? So now let's play the game. We read left to right, and it says exists algorithm. So now the prover has, because it says exists algorithm, the prover has to come up with an algorithm that works, right? So if this problem is computable, then the adversary comes up with an algorithm that solves it. But then the adversary says, oh, I'm trying to prove it's false. I don't think it is computable. So the adversary studies the algorithm, right? Because the algorithm came, and the adversary studies the algorithm and comes up with the worst case input for which the algorithm doesn't work, right? And then the prover wins. Oh, there's another N. Sorry, I wasn't good at getting rid of all the N's. So here, this is supposed to be an A. The algorithm wins on this input. The algorithm wins this game if this algorithm, this machine, gives the correct answer on I. Right? Everybody get the game? And this is exactly how we do computer science, right? If you've done any coding, some boss gives you a problem P, and then you come up with an algorithm A, and some adversary gives you an input I, right? That's the game that we all play in computer science, so we should be familiar with it. Here I'm saying is P is free because it's not bounded by a quantifier, and so the sentence says something about P. It says P is computable, all right? And in fact, so now we want to say, what does this mean? Well, it means that P is computable. And if P is computable, then the prover can win. And if P is not computable, right? So if P is computable, then the prover can supply an algorithm that works. And if the prover gives an algorithm that works, then the adversary can't give a counter input, and so the prover wins. Right? Does that make sense? Here we're going to go through. Now what we're going to do is we're going to prove who wins. All right? So the exists A. Now we're talking about compile time versus runtime. I just made these slides yesterday. So here, let's see. I'm really big in 2001 of focusing on compile time versus runtime. All right. So when we come up with the algorithm, right, that happens before you have to type in the Java code before you compile it. So what happens before you compile it? Well, you don't know the input when you compile it, right? And what do you have to do? You have to type in the Java code. You have to fix what the code is. You have to fix which variables it has, right? All those are the things that are done pre-compiling. We call that compile time, right? And now, once we fix the algorithm, right, then the adversary knows what the algorithm is. And you can't change the algorithm. You can't change the code. It's been compiled. And then the adversary comes up with an input. And this is what's happening at runtime, right? The input is specified at runtime. And after you know the algorithm, and the input can be much, much bigger than the description of the algorithm. And the computation, once it's running, the computation might require a lot more time, or it might require a lot more memory to be allocated dynamically, right? All of these things happen at runtime. Is everybody kind of following?
Sir, I just have one question.
Yeah.
So if in the case that it have multiple, they exist, or multiple for all, would the prover or the adversary be called on multiple times? So
yeah, so if it was there exists an A for all X, there exists the Y for all Z or B, right? Then you would play the game. Multiple level games.
Okay.
And I have, yeah, so we definitely have examples where there's multiple levels. And you can even imagine playing chess, right? When do I have a strategy? Well, whatever you do, I have a move. That whatever you do, I have a move. Whatever you do, I have a move, right? That's how you play chess, right? Does that make sense?
Yeah.
All right. So we want to understand compile time and runtime a little bit better. So I had a question that I was going to put on your test, and instead I decided to make slides about it. So here, let me even tell you, this is the first question that I was going to put on your test. And so what's the test going to have? A lot of things. It's going to have sentences. Yeah, it's going to have sentences like this. I was just remembering I'm putting together a test for 2001 and for 1090. And both of them, their first question looks very much like this. All right, so we want to say, well, what does this, are we going to, oh, no, not like this. We're going to expand it out to something else. All right, we're going to expand it out so we can talk about compile time versus runtime. All right, so what am I saying here? Well, given an algorithm, which is, given a piece of Java code, there's some number of lines of code, right? You can count the number of lines of code, right? So here, let's have a new relation which says lines A on I is going to represent some integer K, where K is the number of lines of code in algorithm A on input I, right? Does that make sense? Now, some of you might notice, but excuse me, the number of lines of code I have in my program doesn't depend on I, right? Doesn't depend on the input. And we'll say, yeah, that's what we're trying to say, right? We need to give it the chance that it depends on it so that we can later state that it doesn't depend on it, right? Now, also, what about time? Well, time does depend on the input. So here we'll have this notation. Time AI tells us how many time steps algorithm A on input I, right? Everybody get our notation here? Oh, this is just a little popping up. This is my father. This is me. And my father is credited with talking about polytime and stuff. So I bring him up sometimes. All right, so now here I'm adding in here these extra statements, right? What's all here? It says algorithm A solves the problem, and the number of lines in algorithm A is K, and the running time of algorithm A on input I is T. All right, so now we have these new variables, right? There's this variable K here, and we gotta fit it into our logic, right? So again, is there at least one K that works? Or does every k work? Right? No, it's not every k. There's one k. This algorithm A has some number of lines. There's only one k that works. So it's an exists. And similarly, time. Does the running, is there any amount, does any amount of time works? No, there exists one running time that works. All right, so now we have these two things, and we got to stick them in. Where do we stick them? Do we put them at the beginning? Do we put them here? Do we put them here? Right? So we think about it, and the prover is going to choose, because it's an exists, right? We know it's an exists, so we know the prover gets to decide it, right? The prover comes up with the algorithm, and then the adversary comes up with the input. And when does the prover choose the number of lines in the code? Well, he chooses the number of lines in the code when he writes the code, right? When he designs the algorithm, he comes up with the number of lines. And as we've said, the number of lines doesn't depend on the input, right? So we put the exists of k up here before we know the input, right? We have to decide what our algorithm is going to be and how many lines of code it's going to be before we can come up with an input. So then what about the running time? Who gets to choose the running time? Well, it's an exists, so the prover gets to choose it, right? The prover chooses it. When they design the algorithm, you're kind of deciding the running time of the algorithm, but the running time also depends on the input. So it's during running time that we choose the input, but the prover gets to choose it after the input comes, right? So let's stick it. We're going to stick exists. Here, people were asking, can you have layers of exists and for all? And so here we have an exists for all exists. Right? Does that make sense? Now here's a question. The exists k, does it go at the before the exists a, or does it go after the exists a?
After?
Does it matter?
Does it go both?
I think it matters.
Oh, right. So here's a general theorem that switching the order of exists doesn't affect things, right? It doesn't matter because the prover gets to choose A and gets to choose K, and the prover knows what the prover's doing. So it doesn't matter whether the prover chooses A or chooses K first, right? So it doesn't matter where we're putting it. So sometimes when I've typed it up, I put the K here, and sometimes I put the K here. Right now I'm putting it there. All right? So now what you might have to, so that on the test, you're going to have to do two things. Some of the questions are, I give you English, and you have to come up with a first order logic statement. And some, I give you a first order logic statement, and you have to come up with English. So let's do it now. If I give you this first order logic sentence, let's try to understand what it means. All right? So first off, here's the whole thing, right? We just narrow it down just to the inner part. And what does it mean? Well, it means that on input I, algorithm A solves problem P with K lines of code in time T. Right? Everybody get that? That's what this says. Right? Everybody good? If I'm going too fast, then somebody say poly, which is slow down. All right, so now I might add on the exists first and then the input first, but I put them both here at the same time. Now, see, now the input is no longer a free variable and the time is no longer a free variable, right? So what does this say now? Well, it says something about A, the algorithm, and something about P, and something about K. And so what does it say about A, P, and K? It says algorithm A solves problem P with K lines, right? And what's implied is it's for all inputs. Now I add a little bit here because it also sort of says, and some amount of time depending on the input, right? So that's what this sentence here says. algorithm A solves problem P with K lines and some amount of time depending on the input, right? So now let's add this exists stuff in front, right? Now there's only one free variable. So what does this say about P? Well, it says P is computable, right? That's what it says. It says P is computable. And more specifically, it's computable with some number of lines of code that doesn't depend on input and some time that does depend on the input. Right? Everybody follow this? So if on the test, if I gave you this, then somehow you have to work out what this says, like this, right? All right, so now another thing I want people to do on the test is to play the game. I want you to know who specifies what in what order, right? Who comes up with the algorithm, who comes up with the K, who comes up with the I, right? Explain which values to depend on which. Well, the values depend this way. A comes first by the prover, and then K, well, you could say K depends on A, but really these two come at the same time, right? And then the I depends on A, and the T depends on I, right? Now explain how these little nuances of the game affect the game and affect who wins the game, right? And then what is being said by the sentence, right? That's what you need to be able to do. And we're going to have another slide later which says, okay, well, who wins? Is it true or is it not true, right? All right, but let's do this first. Let's go through the game. And this is the kind of thing I'm going to want you to say. I'm going to say, well, first we get the exists A. So what is that? Well, the prover is invested in proving that the sentence is true. So the prover gets to produce the exists objects, right? Well, the prover starts by designing the algorithm. All aspects of the algorithm, it gets to come up with the code and it comes up with its variables. And what's important is he has to come up with the algorithm before he knows the input, right? Because we don't want the input to depend, we don't want the algorithm to depend on the input, right? He needs one algorithm that works for every input. And then, well, when he's coming up with this algorithm, one of the things he has to come up with is he has to say, well, how many lines of code can I have, right? So he has his algorithm, he's going to count the number of lines of code, and that's what K will be, right? And why does the prover get to choose the number of lines of K? Why does the prover choose the K? Well, he gets to choose the K because not all Ks work, right? If your K is too small, you can't come up with an algorithm with too small lines of code, right? Not all lines of K work. And he's invested in proving that there's at least one value of K that works. So his job is to prove that this works. His job is to come up with a K in which the sentence is true, right? Everybody kind of follow that? And then, now the for all I, the adversary, we didn't have a little circle for him. The circle didn't come up. Anyway, the adversary is invested in proving that this is false, right? Or to give the prover a hard time. So he gets to choose, when he comes up with the input, he knows the A and the K, and he gets to choose. So now the algorithm has been fixed and is known by the adversary, and the adversary gets to choose the input. It gets to choose the worst input for the algorithm. The adversary studies the algorithm and comes up with the worst case input, right? And now we come to the exist T. So who gets to choose that? We're back to the prover, right? The prover gets to choose the running time when, after knowing the input, right? The number of lines of code he has to choose at compile time, not knowing the input. But the running time, he gets to choose knowing the input, right? Does that make sense? All right. And then who wins the game? Well, the prover must, in order for the prover to win, the prover shows that his algorithm solves P on this input, and the prover must show that the algorithm has K lines of code. And here's a little note that this proves that the K is independent of I, right? Here's a question you might ask: why does this prove that the K is independent of I? Well, because had there been some input for which K was different, right? If K depended on I, there would be an I where the K was different. And the adversary, remember, he wants to win. So the adversary chooses the worst case I, would have chosen an I where the K was different, right? And so together, that proves, since we don't know, since I can tell you the K before I know I, that proves to me that the K is independent of I, all right? And we say K is constant. And whenever I say something's constant in a program, what I mean is that it doesn't depend on the input. All right, so now the running time, the prover also must argue that given this algorithm, this input, it has this running time T. All right, and later in the course we'll talk about how T is a function of I. How does the time depend on I? All right, so now let's go back to what our test questions can be. I might also ask, is A true? Is this sentence, remember I told you this was the first question. So this was question A. So that's what the A is. Is A true or false? Explain to me whether it's true or false. And how do you tell me whether it's true or false? Is you decide whether the prover or the adversary wins the game. And if you say one of them wins, well, then you can give me a strategy, a winning strategy in which that player wins. All right, so here, this is what we're going to do in the test. You're going to say, okay, I'm going to say who wins. Well, if P is computable, then the sentence is true, and hence the prover can win, right? And how do we make the prover win? Well, here's the prover. What is the prover going to do? Well, the prover knows that P is computable, so he finds an algorithm that computes it. And he counts the number of lines, and he lets that be K, right? And now the adversary, what does the adversary do? Well, the adversary is sad. The adversary knows that the prover's algorithm solves P and has K lines. So the algorithm's sad, knows he's going to lose. But to be a good sport, he provides an input, right? He provides some hard input. And then, how about the running time? Well, the prover takes this algorithm and sees how long it runs on this input I, and he figures out what the time is, and he reports the time, right? And because all of these things are true, the prover wins, right? Does that make sense? Now, on the other hand, if P is uncomputable, then the sentence is false. And so who wins then? The adversary wins. How does that game go? Well, the prover goes first, and the prover is now sad now. The prover knows that P is uncomputable. So what does uncomputable mean? It means it has no algorithm. There's no algorithm that can compute it. So he can't come up with an algorithm that works, but he does his best, and he comes up with some algorithm A that he feels is a good try, and he counts the number of lines K, right? Then what does the adversary do? Well, the adversary knows the algorithm, right? Some algorithms might work on this input, and some algorithms work on that input, but no algorithm works on every input. So now the adversary knows this. The adversary knows this algorithm, and the adversary knows it can't solve P because no algorithm solves P. So what does the adversary do? He studies the algorithm, and he finds an input in which the algorithm fails, right? And then again, the prover reports the running time for this input. And however, the algorithm doesn't give the right answer, right? And so this is false, and so the adversary wins, right? People understand that?
Could you go back to the P is
P is
Computable, just the one before this.
right. So in this one, P is computable, and so the prover can come up with an algorithm that computes it, right? If
Yeah.
P, for example, is sorting, then the adversary can come up with the algorithm being insertion sort. And then the adversary knows insertion sort, and he has to come up with some input. What's the input? It's some number of lines of code, some number of numbers, right? The adversary comes up with an input that needs to be sorted, and the prover says, oh, look, if you have n numbers, I sort in n squared time. So you gave me 100 numbers, so it's going to take me 100. 100 is, what is that, 10,000 time, and he wins. Does that make sense?
Yep, thank you.
But over here, maybe P is the halting problem, and no algorithm solves the halting problem. Right? Does that make sense? Did this help people?
Professor, I had a question.
Uh-huh.
So regarding the function lines and the function time, we're making some assumptions on the way it works. Would we be given strict definitions for the test?
There's a good question. I think I go over and look at the test again, and you know that the joy about a 24-hour test is if you don't understand anything, you can talk to me about it. In fact, let me report right now. We have a tutorial at this time on Friday, right?
Yes.
So what I'm recommending is everybody read over the test in the morning. You get the test at 8 o'clock, and you try to solve the problems. You try to think about the problems. And then during the tutorial, we're going to have a tutorial, right? And what are we going to do with the tutorial is I'm going to start by reading the questions to you and making sure everybody understands the questions. Because I'm shocked sometimes, even though I think I'm the most brilliant writer of all times, sometimes people don't understand the question. So if I say here lines, then I have some meaning of what lines means, but maybe you don't understand it, and so so we can discuss it at that time, or you can email me at, you know. But I think it's always, I try to always explain my terms, so I probably did.
Okay, gotcha. So if we had any clarifications for any functions or predicates, we can ask during tutorial.
Yeah, or I'll be around all, you know, I'm always around, so you can write me.
Perfect. Thank you.
So, Professor, I have
yeah.
a question.
Yep.
So for this slide and for this kind of question,
Yeah.
do we have, if it's asked in a test or assignment or whatever
Yeah.
it is, like for 24 hours,
Yeah.
so do we have to lay out like two cases of this question that, okay, if P is computable, then this is the prover and adversary thing, and then same for the uncomputable case?
Yeah, that's a good question. I confess that in my
Or
yeah.
we would be given like a question like you said, insertion sort or halting problem, and based on that we're gonna have to play the game.
Right. So trying to remember what I asked. I think I asked one, tell me what the game is, and tell me why it matters, the order in which you do things, and why having this order matters. And then as a separate question saying, well, if it's true, how do you proceed and have the prover win? And if it's false, how do you prove that, how do you show that the adversary wins, right? And I think when I wrote it up last night, and I think I always showed how the prover would win if it's true, but I don't think I wrote how the adversary would win if it's not true. But maybe I'll go back and type that in as well.
Okay, because I'm kind of confused that how do we exactly know with this kind of question if the problem is like the P is computable or not? Because I think the whole thing depends on it. If it's computable, then how do we play the game and stuff? So
Yeah. So any sentence, so most sentences that we're going to be talking about, whether it's true or not, if it has free variables, right?
Yeah,
In this case,
okay.
P is a free variable. Whether or not it's true depends on the free variable.
Okay.
And when I say, what does it mean? Well, what does the sentence mean? What it means is, well, if it's true, which P's is it true for, and which P's is it false for? And in this case, it's true for those P's which are computable, and it's false for P's which are uncomputable, right? So what does the sentence mean? What it means is that P is computable.
Okay.
Professor,
Yeah.
I just have a quick question regarding the website. So here it says number 1 predicate logic 1090.
Right.
Like where you said the videos that we have to watch.
Right.
So why does it say 1090? Like on
In
the
brackets?
yeah.
All right, because the first PDF. So when last time I taught 2001, the first PDF are the PowerPoint slides that I used in the first week of teaching 2001. All right, and the videos that are posted are the videos recorded in either last term or the year before. So that's what those are. Now, what's in brackets that says 1090 is because I'm teaching 1090 for the first time this term. And so I spent the whole summer making new slides. And I mean, the slides we just looked at today, for example, I made most of them yesterday afternoon. So you won't find those in the PowerPoint slides from last year, because they weren't from last year. Where are they actually? They're in the 1090 slides. And so
so these videos that are in this section, if we only watch these videos with the notes that you're just showing us, they will be enough for the test?
Yes. Yeah.
Okay.
Yeah.
I have a question.
And the 1090 slides, it's the first dot is the new version of these slides. So it's very similar to what the slides you were from last year, except, well, I revised them over the summer. So they're.
And are you gonna post these slides? Like, where can we find these slides that you're explaining on them now, like on the website?
All right. Well, let's go to the website, and that's what I'm saying where they are. So in 1090 slides, they're down here at informal understanding. All right. But if we go over to our course, then let's see if this link works. We come down to first order logic. Oops.
So I don't think the website's showing on the screen. I don't know
Oh,
if that just
we're not seeing it.
All right, sorry. Sometimes when I share screen, I click on the PowerPoint and then only the PowerPoint links. But somebody talked about how if you go to the 2001 slides, it's 2001 webpage, it says predicate logic, and then it has some PowerPoint slides, and then it says 1090. And then it has 3 links, all right? So if you go to the first link, it comes down and says 1092, informal understanding improves, right? So if you download that, then what you get is these slides. And if you go to the first page, here's the first page.
Are you talking about the 3 files that are inside the bracket? beside
Yes.
the word 1090?
Yes.
Okay.
The first one is this set of slides. It's the first set of slides that I think would be useful for 2001. And it gives you this, and if you come down here, that's where it says computing. That computing and compile time versus runtime is what we just did. Right? If you hit F5 and then you hit compile time, there, see, this is the slide that what we just did. Does that make sense? Is everybody good?
One quick thing.
Yeah.
So, like, are there some problems where we're not sure whether it's computable or not?
Yes, but you don't need to, on the test, you don't have to know. I'm not giving you a problem.
Right. I was
I'm
just
giving
wondering.
you the sentence, right?
Yeah.
Right now, we're not caring about problems. We're caring about this first order logic sentence. So, and it's this sentence, what is it doing? It's defining computable, right? What does computable mean? It means before we can come up with a particular problem and whether it's computable or not, we need to know what computable means. And this is the definition of computable. Right? What does it mean? It means there exists an algorithm and all inputs that gives you the right answer.
Your mic.
Everybody good?
Yeah, you're good, sir.
All right.
Jeff, I have one more a question about that the last one where you had a part where it's computable and not computable.
Yeah.
So I was wondering, like, if I were to do that question on a test, and
Yeah.
on 1090 you have a domain and a interpretation.
Yeah.
So if I define the domain of the algorithm and the problem to have only valid inputs, or like inputs that allow the problem to be computable, would that be okay for the answer? Like, so then I don't have to consider the other case where the input makes the problem uncomputable, or like it doesn't halt. If I do that, is that okay?
No, I mean, the other person asked about that on the test, and I don't think I've included it yet, but I'm going to go back and include it, right? I mean, maybe we could say, you're trying to tell me what this sentence says about P, and it says that it's computable. And what is it? So what does that mean? Well, when P is, quote, computable, the algorithm can win. And when P is not computable, the adversary wins. And so I think it'd be a good thing for each example. I have 5 examples right now on the test. I don't know if that's too many, and I don't know whether some of them are too hard for you. But what I'm hoping is people will say, well, given this first order logic sentence, what's the game? And I want you to kind of convince me. I don't want you to just say, well, the prover gives me A, and then the prover gives me K, and the adversary gives me I, and the prover gives me K, because a monkey can read that off, right? You want to give me the nuances of the game, right? Why does the algorithm get fixed first? Well, because it can't depend on the input, and because we need to have one algorithm that works for all inputs, right? Why does the time come later? Well, because it's at runtime, and then it depends on the input, right? You tell me some nuances about what you understand from this, right? And then you kind of say, well, what does it mean? Well, the free variable is P, and so what is it saying about P? And then you'll say in English, oh, well, it seems to me it's telling me whether P is computable or not, right? So then you can say, well, if P is computable, how does the adversary win? And if P is not computable, how does the adversary lose? And, right, and if you're nervous, you can give concrete examples. You can say, oh, well, if P is sorting, then it's definitely computable. And what the adversary is going to give, what's the algorithm is going to give, is going to give me insertion sort, right? And then maybe you don't know about uncomputable problems, but I'll tell you right now, halting is an uncomputable problem, right? So, and for halting, any algorithm you give me has an input in which it's going to fail.
Okay, gotcha. Thank you.
All I'm looking for is, so what I want to know that you understand this first order logic sentence, right? So I would say just give me as much as you can think to give me to convince me that you really deeply understand the nuances of this first order logic sentence, right? And so what can I ask? Well, I can ask, well, can you, those are what I asked.
Professor?
Yeah.
Yeah, so I just wanted to confirm, so there is no hard or fast rule that just says if the problem is computable or not. It's all about how we present our arguments and lay down our points to explain if a problem is computable in fact or not.
Well, no. I mean, this here is defining what it means to be computable. If there's an algorithm that works for every input, then it's computable. If there's not an algorithm that works for every input, then it's not computable. This is the definition of computable, right? Okay. And what I'm wanting you to get is to be able to read this, and just reading this alone, if I gave you this all by itself, I want you to be able to figure out, oh, this is asking P's, what I want you to learn to be able to do is say, what are my free variables? Oh, look at P is not quantified. So what does this say about P? Well, for some P's, this is going to be true, and for some P's, it's not true. For which ones it's true? Well, it's true when there exists an algorithm that's for all input, it gives me the right answer. So what is this saying? This is saying P is computable, right?
Right, thank you.
And it's not like we're going to be talking about it right now. We're not talking about a specific P, right? If you need examples, well, P could be sorting or P could be the halting problem. But we're not talking. But that's not our issue now. The issue is knowing what this says, right? And you'll note I don't give you a particular problem, so it's not like you have to prove ever in this question. You're not proving that insertion sort solves P, right? I mean, in fact, the danger, if you named here a specific problem, say sorting, then you would be tempted to name a specific algorithm, like insertion sort. And then in the proof, you'd be tempted to talk about the algorithm, right? On a specific input. And we don't want to do that, right? You'll see my proof down here. I don't talk about a specific problem, right? It's all very abstract. If P is computable, then by the definition of computable, we know that he can find an algorithm that computes it, right? What does computable mean? It means that there's an algorithm that can compute it, right? And that algorithm will have some number of lines of code, right? Well, if this algorithm doesn't compute it, what does it mean? It means it doesn't matter which input the adversary gives, we will always get the right answer, right? Everybody just kind of see this proof, what I'm saying here. It's just more ways of explaining how the definition of P being computable, right? That when P is computable, this sentence is true, and when P is not computable, this sentence is false, right? Does that make sense?
Professor, I had a doubt regarding one of the questions in the recordings regarding computability. There's a question saying it's a true or false, saying for all inputs there exists an algorithm for which A of I is equivalent to P of I. That's algorithm of input is equivalent to problem of input.
All right, could you say it again because it went too fast for me?
There exists For every input, there exists an algorithm for which A of I is equivalent to P of I.
For all I, there exists an algorithm such that it works.
Yeah, it's a true or false. I can see why it's true, but there's one thing you said in earlier, that there cannot be different algorithms. But in this case, if we see that, it's saying that there can be, because input is first, and it's given as true in the slides.
Yeah.
I didn't quite get
Yeah.
it.
Here, let me come up here and answer that question for you. I have slides about that in these new here.
You probably need to share your screen instead of the PowerPoint, because we're still seeing the old PowerPoint.
Oh, but that's what I want to show you. I'm showing you this PowerPoint. All right, so here's my new slide.
No, we're still seeing the one that says logic for computer science, syntax, semantics, and complete.
Oh, okay. I don't know why that is, because
the easiest way might be to just stop sharing and just start again.
Yeah, exactly. Here, stop sharing, and then share screen, and I'm sharing this screen, which I think is what I did last time, but maybe not. All right, do you see our picture from Clockwork Orange?
Oh, yeah, sir.
All right, so if you haven't watched Clockwork Orange, it's a scary movie when I was little. All right, so what I want to do, so what they did in the movie is they tortured him so that he would get upset when he saw things that should upset him. So here, when you see things like this, I get physical pain. This sentence hurts me because it's so wrong, right? Because you can't have a different algorithm for every input. So here, let's kind of go through and see why this is wrong. Well, let's say problem P is you take input X and you square it, right? And we want to say that there's a Java program that solves P on every input, right? That's what we want to say, right? In fact, here is a Java program. And what does this Java program do? It's
We stopped hearing. I think he cut off because his video froze as well.
Professor, no.
Either his battery died or his internet cut off.
computer probably died.
Should be back soon.
Well, there goes that.
Yo, who's ready for the test, man? It's just Friday.
Funny joke.
It's okay, it's okay. It's not that hard, yeah. Just probably for whoever doesn't really understand and hasn't paid much attention, I think it's important to rewatch what the lectures just put, because these are the baby steps of this class. If you're having issues understanding this, you do gotta make sure you understand it, or you're gonna get lost in the middle of an ocean and you're not gonna go how to swim back to shore.
Honestly, you guys need to stop complaining about him teaching 1090 stuff.
You know, this guy is amazing. I met George before, and George, just the way he speaks, this guy is clear. He's using simple words. He's an amazing teacher. We're really lucky to have him for this class.
Oh my God, Xavier, we get it. Your class rep. Relax.
My what? No. But I'm nothing like that.
I'm just messing with you.
It's funny hearing it because I have no idea who George is. So it's funny hearing this like rivalry he has going with this teacher I have no clue about.
You don't want to know who George is.
You don't. Yeah.
I like that he throws it in though, like
guy.
He's like, George said this, but I don't agree. So I'm just doing it my way. I'm like, yeah.
George is literally the worst I think I've seen since I've been in New York. I'm just grateful for Visual Schedule Builder because that's what made me not take George.
Yeah.
For real.
Yeah.
Oh,
he's back.
Oh.
King has returned.
Hi, class quiet.
All right, sorry guys. My computer crashed again. I think that. All right, so let's see. Share screen. We're sharing this. Share. And PowerPoint. All right, so let's go back to what we were doing. All right, so what we want to say is that there exists one Java program that solves the problem for every input. And here's a Java program, and everybody agrees that this Java program squares X, right? On the other hand, what is this saying? This saying is for every X, I have a different Java. I can have it. It's possible I have a different Java program, right? So here on input 1, my Java program returns 1. On input 2, it returns 4. And on 3, it returns 9. And 4, it returns 16, right? So this is saying I have a different Java program for every input. And this is wrong, right? So on a test, I can very much imagine saying, tell me what this means. And what you guys would say is, I feel pain like it was Clockwork Orange, because this is clearly a horrible sentence in which it says every input has a different Java program. Right? Does that make sense?
Professor, you, in one of your lecture recordings, said this statement is true.
Oh, it is true. It is true. It's just, it has no meaning. It's true even if P is the halting problem. It's always true, right? Here, how can I prove it's always true? Let P be even the halting problem, right?
No, so I get it how it's true, but in exam, so we need, in tests, we need to write that it's true.
Yeah, so if I say, what does this mean? What does this mean? Is it true? You would say, well, it's always true. And what does it mean? It means that, why is it always true? Because what it means is that for every input, you can have a different Java program. And that Java program could just give the answer for that input. And so is it true? Yes, it's true. Is it meaningful? Does it say something that we like? No, it doesn't. Does it fill us with pain? Yes, it does. Right?
Yes, sir. What you're trying to say is, like, a syntax-wise, if we have to say if it's true or false, it's true, but semantic-wise, it's not. Like, is it like that?
Yeah, I guess so. In terms of meaning, in terms of truth, it's true.
True, yeah,
In
but
terms of, does it say
meaning-wise,
anything useful to us? No, it doesn't. You say,
okay.
what does it mean? If I ask you, what does it mean? Well, it means something that's not useful to a computer science person.
Okay.
Sir, I understand what you mean by the whole for every input, but what exactly is the table for?
Oh,
Like, the code?
yeah. So, see, is there a Java program that takes input 3 and outputs 9, right? This says for every input, say 3, there's a Java program that the Java program outputs, well, what should it output? It should output 9. So it should output 9. Okay, right there. Is that a Java program? You can see my mouse, right? Is that a Java program that on input 3 outputs 9? Yes, right?
Yeah.
And here's a Java program that on input 4 outputs 16, right? So every input has a Java program that gives the right answer for that input. But it's a different Java program for every input.
Okay.
Right? So when we do computer science, we don't like this, right? We like this. What's this? There exists one Java program. Here's one Java program. And what does it do? It solves on every input. It solves this problem.
So, is it possible that we were given a different output and it'll still be true?
What true? I didn't understand the question at all.
Is it possible we have a different output than to make this statement false?
Make this statement false? Well,
yes. And how do we prove it's false?
Well, that's the thing is, if you're interpreting this as a Java program and this is a problem, I'm saying it's not false. It's always true. I guess it's always true.
No, what I'm saying is if the output isn't x squared, if it's something else that the statement would be false, how exactly would we prove it's false?
Yeah, but I'm saying you can't prove it's false because it's always true.
Oh, okay.
Right? How is it always true? Well, let me prove that it's always true. Let P be any problem. What's a problem? For every input, there's some required output, right? That's what a problem is. Given any input, there's a required output. So we know what P is. All right, so now I'm going to play this game, and I'm going to be the prover, and you can be the adversary, and I'm going to show to you that I always win. Right? No matter what this P is, I'm going to always win. How am I going to win? Well, you start by giving me an input X, right? And so I come down here and say, well, if the input's X, what's the required output? And then I have to come up with the Java program. So I have the Java program. What does it do? It ignores the input and outputs the required answer. So what do I do? Now I have a Java program that gives the right answer. Right? So I win the game. Now you might, did you follow that?
So it ignores the input, but just outputs the right answer?
My goal in this game, I know your input. So my goal is to come up with a Java program. It doesn't have to give the right answer for every input. It just has to give the right answer for that input. So here's a program that gives the right answer for 3.
Okay.
Right?
Okay, thank you.
Professor, I had a question regarding this. So I understand why this is, it's not really saying anything in this context.
Right.
But for example, let's just say we were given this without any context. Could we say that this statement is saying that P is computable?
No, because computable, I'm hoping that you'll get that computable means that it has an algorithm that works for every input. I mean, I also give you some meaning here, right? I told you J is a Java program, and I told you that X is an input, and hopefully you'll be able to interpret everything that's there. And so I'm wanting you to interpret what's there and see if it means something to you in your life, right?
Gotcha. So in this case here, computable isn't just it has an output for a certain input. It means it has a certain output for all inputs?
Yeah. This is what computable means, right? Look at the difference. This and this are exactly the same, except we switch the order, right? Order matters.
Okay, gotcha. That makes sense. Thank you.
In this one, there exists one Java program. So if I touch it, it moves.